A very good evening, Professor David Wineland.
Thank you.
Okay,
Good morning. Good morning
okay.
to you.
Okay, good morning, sir. Good morning. Good morning, all of you. Today, it is my privilege to welcome Nobel laureate Professor David Wineland. Before starting the session, I would just like to brief about him. Professor David Wineland received a BA degree from the University of California, Berkeley in 1965 and a PhD from Harvard University in 1970. Following a postdoctoral position at the University of Washington in Seattle, he joined the Time and Frequency Division of National Institute of Standard and Technology in Boulder, Colorado from 1975 to 2017, where he was a group leader and NIST fellow. He is now a Philip H. Knight Distinguished Research Chair and a research professor in the Department of Physics at the University of Oregon. Starting with graduate school, a long-term goal of his work has been increase in the precision of atomic spectroscopy, the measurement of the frequencies of atoms, characteristics, vibrations. This research has application to making better atomic clock and has led experiments that enable precise control of atomic energy levels and atomic motion. Such control can be applied to meteorology, whose precision is limited only by the constraint of quantum mechanics, and to demonstrations of the basic building blocks of a quantum computer. For this work, he shared the 2012 Nobel Prize in Physics with Serge Haroui, Collège de France, Paris. Now, the floor is yours, Professor David Wineland. You can start.
Okay, well, thank you for the introduction. You can see my first slide, okay, is that right? So, can you see my presentation?
Yes, yes. Yes, it is clearly visible.
Okay. All right, thank you. Well, thanks for the introduction, and just a brief summary of what I'll talk about is, first of all, why do we want precise clocks? And I'll then say a little bit about the basic ideas about how atomic clocks work. And these days, we're interested in optical atomic clocks, that is, their oscillations are at optical frequencies. And I'll try to give you all an idea of kind of where we're at and what the future might hold. So actually, to answer the first question, for many centuries now, clocks have been used in navigation. So that's still one of the basic applications. So in traditional navigation, before we had electronics and so on, we used particularly sailors at sea would use a sextant to determine for example, can you see my cursor, by the way? My pointer, rather. Sorry, can you see my pointer?
Yes.
Okay,
yes.
Thanks. Okay, so the idea for finding latitude, that is where we are on the Earth in terms of north and south, the idea is pretty simple. That say a sailor or a person standing on the Earth, he needs to look at a star. We typically think about the North Star, but and if he determines the angle between his level position and the direction of view to the star, then that angle theta uniquely determines where we are in latitude. And so the thing about what about longitude, that is east-west direction. And for that, the idea is exactly the same, except since the Earth is rotating, then we have to know what time it is to know where we are relative on the surface of the Earth. And so we use some other fixed star, but basically we again measure the angle, and if we know the time, then that tells us where we are in terms of east-west longitude. So errors, to give you an idea, errors in position, we can do a little simple calculation where error in the, pardon me, in longitude, the error in distance is given just by the radius of the Earth times the error in the angle, and just plugging in the numbers for the Earth for the Earth's rotation. The frequency is once per day, and then we can arrive that if we desire 1 second timing, then that requires that would give us about a quarter of a nautical mile in terms of precision in longitude. And there's a long history about this. There's a good non-technical book that I like that it doesn't have very little technology in it, but it's a nice book to read to give the history. Sorry. So the idea of pardon me, these days, of course, we navigate with satellites, and the idea there is very simple, is that we will have a network of satellites, but the idea is by some prescription, if we have synchronized clocks, that is, you as an observer has a clock that's synchronized with the clock on a satellite. The idea then is that if by some protocol, it's more complicated than this, but let's say we agree that the satellite will emit a pulse of radiation on every second tick, then we know, just because the time delay due to the speed of light, receive that pulse at a time t1, which is a little later than the time when the pulse is emitted. And so the distance from the satellite is just given by the speed of light times this time delay. And to give an idea of the errors there, what the errors in timing give there. So if we can get a nanosecond timing precision, we can actually get down to an uncertainty in the distance here of about 30 centimeters. And this also gives an idea of this timing precision gives also an idea. It's approximately equal also to the frequency and precision. That is how rigidly we have to hold the frequency to perform these measurements. Of course, this only gives us one distance, the distance of one satellite, and of course the way that the GPS satellite system works is there's a network, and if there's at least 3 in view, then you can get your 3-dimensional position, and also allows you to get time by synchronizing the clocks. And so typically, I forget how many satellites there are visible at any time, but it's more than 4. So the system's somewhat redundant. It can do self-checks to get to make sure it's working correctly. So what about clocks? And the idea is, pretty simple. We just want some periodic event generator, and if we then count cycles of this event generator, that naturally gives us a time scale. And so the traditional periodic event generators are, for example, a rotation of the Earth once per day, and later, starting a few centuries ago, people started using pendulum clocks, and actually pendulum clocks can be quite good, but not quite as good as our electronic clocks we have today. But it still has the basic idea that we want some periodic event generator that we're going to count cycles of. So atomic clocks the atomic oscillations just act much like a pendulum clock. That we can think of a simple case is where this is for an optical transition. But let's suppose we have an optical oscillation in our atom. We can think of a charge that's oscillating back and forth, around the center of the nucleus. And of course, being physicists, we like to think about the wave mechanics, and actually the electron is not well localized. It is in this classical picture down below. It's kind of smeared out. That's the wave function that's oscillating. Nevertheless, it has an oscillating electron density that gives rise to an electric dipole radiation. And this frequency then, if this frequency is determined by the difference in 2 energy levels of the atom, then that frequency is given by the energy difference between the two levels divided by Planck's constant. So actually, one version of clocks is what we call masers or lasers, and I think everybody's familiar with a laser. The M in maser just stands for microwave, so they work on exactly the same principle. It's just that the masers work at microwave frequencies, and in fact, the first laser type devices were actually masers. The maser principle, the laser principle was shown first in microwaves. So anyway, we have our oscillating, charge that emits radiation frequency at some frequency, and the idea is we typically the way a laser or a maser works is we have some cavity surrounding the collection of atoms. And the reason we do that is that the cavities, this is more valid for the laser case maybe, but the idea is we can build up a traveling wave that's going back and forth. So we make a standing wave, and we want to synchronize that standing wave to the oscillations of the atom. And then when that is done, we take a little bit of light that's transmitted through one of the mirrors and then count the cycles of the radiation. So just to give you a little idea of my history, so I was a graduate student from 1965 to 1970 at Harvard, and my thesis advisor was Norman Ramsey. He's actually one of the most famous atomic physicists in the 20th century. Anyway, here's Norman Ramsey, and that's me getting close to the in my younger days. Whoops, sorry. Anyway, this was our group at that time, and so Norman wanted to. He and his colleague Dan Kleppner, who later went to MIT, they had invented and demonstrated the first hydrogen masers, so I was in the group not long after this. They demonstrated the first hydrogen masers. And so Norman wanted to have the frequencies of all three isotopes of hydrogen built into a clock. So my topic was to make a maser based on deuterium rather than hydrogen. And the principles were very much the same, but there was some differences because the wavelength of deuterium is substantially longer than that of hydrogen. So anyway, so basically, what we do is that we, as I say, we put in this deuterium or hydrogen case, the atoms are a collection inside this cavity, and the problem that the cavity helps us build up the radiation to sustain the oscillation, but a problem is that the cavity may not be exactly at the same frequency as the atoms. And if that's the case, then the output frequency is, we say it's pulled by the frequency of the cavity. And there are ways around to ensure that the cavity is at the same frequency of the atom, but they involve some complication, which I'm not going to go into here. So I'll give the idea of typically the way we do it now. And so the more common mode of operation that basically all the precision clocks use is we have again our clock is going to be based on a transition between two energy levels in the atom, and we'll put the atom in the lower state first, and then we'll apply radiation at a certain time close to the transition frequency, and we'll apply radiation, and then after the radiation is applied, we'll measure the probability of the atom making the transition to state 2, and the maximum transition probability is just then given by when the frequency of the source here is equal to the frequency of the given by the energy difference by Planck's constant. And so then if we can meet this condition, then we just count cycles of the source rather than looking at the radiation from the atoms directly. And of course, for precision, we'd like this transition to be very narrow in have a very narrow absorption frequency. And the reason we want that is only that we can then, we're very sensitive to where the radiation source is tuned. We're typically, we want a narrow slope here to be able to precisely determine. And I said, I distorted the picture a little bit. We don't actually look for the maximum transition probability. And the reason for that is if we sit right near the resonance, the top of the transition is fairly flat. So the way that all the clocks typically work now is we'll first probe with a radiation on one side of the resonance line. And then after that, we'll probe with a radiation on the other side of the line. And we want the response to be equal. And when the response is equal for both frequencies, then we know that the mean frequency of the two probes is at the resonance frequency of the atom. So that's a little detail, but it's to get around the fact that, as I say, if we probe near the top of the resonance, it looks very flat. So why atomic clocks? And I'm going to compare here to the case of a pendulum clock, but we can, the same considerations come in, for example, with a quartz crystal clock. And but I'll just use the example of the pendulum in this case. In first physics classes, you'll learn about the frequency of a pendulum clock, and it's basically the frequency for small amplitudes is given by this expression here, where this is the gravitational acceleration, this is the length of the pendulum, and that does that's what sets the frequency. So one thing we have to worry about is environmental sensitivity. And so in the pendulum clock, we have to worry about the length of the pendulum changing due to temperature. And just to give one example, so that for a given temperature change delta T, then the change in length is given by the length times this coefficient of thermal expansion times the change in temperature. And so even most metals are, for a very good low expansion material, like they're typically some kind of ceramic or glass, the temperature coefficients can be around 10 to the minus 8 per degree C. Most metals are 500 times bigger than this. So, that's why we use these low expansion materials. Anyway, I won't plug in all the numbers here, but that gives a fractional frequency and precision for a change in temperature given by this expression. It's for this example I've chosen here, but it has this actually fairly good low temperature expansion. The clock almost has a frequency dependence of about almost a part in 10 to the 8th per degree C. So the nice thing about atoms is that the temperature sensitivity there, actually I show a little cartoon here, and actually a lot of the early clocks, and still some of the not less good performing ones, they'll have like atoms, they tend to be alkali atoms in a glass cell that, for example, hydrogen was in a glass cell, and it had a coating of Teflon on the inside of this glass, and that was just prevent the atoms from sticking on the wall. Anyway, so we can use this picture here, and the one thing we have to worry about there is the temperature changes can cause an effect that was due to Einstein, and that is that Einstein, one of his great discoveries, he told us that there would be this relativistic time dilation effect. So that if the atoms were moving relative to us, the frequency would be lowered. And then, the profound thing about Einstein, though, is it's not just, that maybe the apparatus causes the atoms to slow down and change their frequency. And what he taught us is really fundamental, is that time is changing for the atoms. So we run it. We in the lab run at a different rate than the atoms perceive time. Anyway, to give you an idea of the size of that effect, I just do a little simple calculation. I won't walk through, but for atoms of mass 133, for example, cesium, the frequency shift due to temperature is about 8 orders of magnitude it's smaller than, pardon me, I said that, about 6 orders of magnitude slower than that due to the pendulum clock. So the other things that, the other things it depends on is reproducibility. So for example, there's manufacturing tolerances, which will change the length of that will have different lengths of our pendulum. And it also, of course, depends on the local value of G. And of course, the bearing up that supports the pendulum may actually wear a little bit to change the length. And so the nice thing about atoms is that basically all atoms of a particular kind, cesium-133, for example, are exactly identical. So, and the other thing is atoms don't wear out. We can, as long as we can keep them around, they're going to be identical forever. And so that's where we get that. That's one of the main reasons for that we used atomic clocks, is the frequency is fixed by nature. To give an idea, I mentioned cesium here. The cesium clock transition, it's called a hyperfine transition. It's just, and there the hyperfine transition is due to the difference in energy that the atom has, and when the say the electron spin and the nuclear spin are parallel or anti-parallel. And that difference in those spin orientations gives a difference in energy, which through the expression of Planck's constant gives the frequency. And so the frequency of cesium was measured to be about 9 billion and so many cycles per second. And in fact, in the mid 60s, the definition of the second was defined as so many cycles of this hyperfine oscillation in cesium, about 9 billion. You could count the number there. And this was the definition made of the second in 1967, and it's still actually the definition. And I'll say a little bit about why that still remains true. So what I'm going to be talking about is atomic ions. And I'll say just a few brief ideas, give a few brief ideas on atomic ions. I won't. So the two inventors of ion traps were Wolfgang Paul and Hans Thejmelt. And they shared the 1989 Nobel Prize with Norman Ramsey, my thesis advisor, for their invention and their work with these ion traps. So I won't say exactly how the operation works. I mean, any freshman student can go through it, but it takes a few minutes to go through. I won't go through that. But basically, we apply a combination of static and oscillating electric fields to this electrode structure, and what that does is, if they're at the right frequency and amplitude, that creates a three-dimensional harmonic well for our ion trapped in the middle of this electrode structure. And you don't really need to know about the physics so much for this example. You can think of the atom in the trap is like a marble in a bowl, and the marble can roll back and forth. In the last decade or more now, we've been interested in trying to make clocks based on optical transitions. And one reason for that is just simply that the tick rate, the oscillation rate that can be very high. And that means we can define any unit of time and have finer and finer divisions due to the time period of the oscillation. And I show this example here of, this was for mercury ion, which I'll say a little bit more now about that case. Anyway, it's a little over 10 to the 15 cycles per second. So this radiation is actually ultraviolet, past visible radiation. So that there's many choices, and I'll give you some idea of the breadth of choices. But this is the one we first went after in our lab at NIST. So actually, is this idea of optical transition new? Is it new? And actually, no. And interestingly, actually, one of my colleagues at NIST, Bill Snyder here, he dug up a text written by Thomson, Lord Kelvin, and his colleague Peter Tate, and they basically, in this text that they wrote, they said the recent discoveries, indicates natural pieces of matter. They're thinking of atoms in particular. In fact, they were specifically thinking about optical transitions in sodium. Anyway, they say, particularly, certain kinds of atoms, readily made in infinite numbers, are all absolutely alike in every physical property, including the time of vibration corresponding to one of the modes of vibration. And it is known to be absolutely independent of its position in the universe and will probably remain the same as long as the particle exists. And actually, they almost got this right. I mean, they certainly had the idea of using these natural occurring, these atoms and so on that would be identical. And the only reason I've highlighted this one phrase in red because they can be excused for this. It's not true because Einstein's theory of general relativity shows that that's not true. And I'll come back to this, but at least they can be excused for not having known that. They certainly had the basic idea. So I'm going to talk about this one example that we work on at NIST in Boulder. And for various reasons, we chose mercury. So that the clock transition in single ionized mercury, 199 here, it has a frequency slightly above 10 to 15 hertz. And it has it, and the basic idea, we're gonna probe this particular transition. This is the atomic physics notation, but you can just, if you're not familiar with that, we just call them level 1 and level 2 here. In any case, we apply radiation to this to our mercury ion, and we of course want to get it to absorb radiation maximally. And in principle, the way a lot of atomic spectroscopy is done is to look at absorption. And in principle, that would work here, except that one atom, one ion doesn't absorb much radiation, so it's hard to tell when it absorbs the radiation. So we do another trick, which is it's fairly common in spectroscopy and certainly in clocks, and that is we have another laser, and it's going to drive another transition in mercury. And this is a strong electric dipole transition. In fact, the lifetime of this upper level in this transition is only a couple of nanoseconds. And so the idea of this 3-level scheme is that we start the atom in the lowest level, and we apply radiation to the transition that defines the clock, and then we turn it off, and then let's suppose the radiation was not in resonance with this transition. So the atom, after applying the clock radiation, it remains in the ground state. Then we turn on the second laser here, and if it's in the ground state, then it'll scatter a lot of light. And conversely, if the atom if the frequency of the laser transition is correct, then it'll promote the atom from the ground state to the excited state. And then when we turn on the second laser here, we don't see any fluorescence. And in fact, actually this effect is amazing. I mean, it's essentially 100% efficient. Whoops, sorry about that. It's essentially 100% efficient detection of a single atom transition. So, and as I say, this technique of so-called double resonance is used a lot in atomic clocks, atomic spectroscopy. So anyway, just as an aside, we can actually see a single atom. Now, in fact, we can't, this transition where we scatter the light, our eyes aren't sensitive to it, but we made a video camera, it was much cruder than one you can buy in a store. But anyway, it was sensitive to this ultraviolet light. So when we shined this laser on, we could see the atom. It's this little speck in the middle there. Actually, one side thing to say about this picture is that the atom where the dot is, that represents that is the atom, but the actual size of the atom, which we can determine by its wave function, wave packet size, is about 500 times smaller than the size than the dot you see in the picture there. So So, and our picture is just limited by the limitations of the optics we have to look at the ion. Actually, I said, we couldn't observe mercury because it's sort of at an ultraviolet wavelength. But for example, other people have used barium ions, and barium ions, the transition, analogous transition there, they actually fluoresce in the blue. And I've been in labs where, people have worked with barium. You can actually see with your eye a single atom, with light focused on it. So anyway, we actually, another little side thing here is that this radiation that we use to detect the transition, we can also use it to cool the ions. And I'll just give a brief description. The idea is pretty simple, and that is, suppose we tune this laser to a frequency that's lower than the resonance frequency. Then when if the atom moves against the laser to the left here, then the Doppler effect will shift the radiation up to higher frequency. And so the atom will scatter, it'll absorb and re-emit, scatter more light when the atom is moving against the laser. On the other hand, when it moves with the laser, the Doppler shift shifts it farther out of resonance. So there's this asymmetry, and when it moves towards the laser, it scatters photons, and the momentum kicks from the scattering will slow it down. If it moves with the direction of the laser beam, it still scatters, but at a much reduced rate. It'll scatter and heat the ion, but the overwhelming effect is when it moves against the laser beam, it can give momentum kicks or slow it down. And so to give a typical example, in the mercury ion, the experiments we ran, at least early on, were all at room temperature, 300 Kelvin. And using this laser cooling trick, we could cool the atoms from room temperature, about 300 Kelvin, down to 1 millikelvin. So it would basically suppress this time dilation shift by about a factor of 1,000,000 relative to what it is at room temperature. Okay, so this is just a little picture. This was after our group just had formed. Actually, the person I did the cooling demonstration with was Bob Drillinger on my left, and then we quickly joined up with Jim Berquist, who is the laser expert, and Wayne Atano, who is our resident expert theorist and computer guy. So basically the four of us worked for a long time together, trying to develop this mercury clock and other things. Anyway, so I'm going to try to get rid of this thing here. I think I'm trying to get rid of this thing that's in my way here. I forgot how to do it. I'll leave it up there. Anyway, we started these experiments on mercury in 1981, and they really it took a long time. They reached their full potential only until around 2005, 2006. And as I mentioned, the clock project, this mercury clock project was guided by James Berquist. We all had our hands in it, and we had students working on it too. So anyway, so just to summarize some of the features we realized, so that the trapping, just the trapping alone means that on average, the average velocity of the ions are 0. So that there's no first order Doppler shift if we average over the absorption signal. And of course, the laser cooling suppresses the time dilation shift, as I said, by about a factor of 10 to the 6. The other thing, in the later experiments, the first experiments were just done in a vacuum cell at room temperature. And we later went to trapping in high vacuum, and we went to had a 4 Kelvin temperature liquid helium cooled cell that held our trap. And one of the main reasons for that was that the environmental, the collisions from background gas, if we were at room temperature, would cause problems, cause frequency shifts, and potentially heat up the ions, of course, too. So that's why we went down to 4 Kelvin, which basically at 4 Kelvin, any of the common gases we have to worry about collisions, they're just, those gases are frozen on the interior wall of the cell we hold the trap in. So another interesting effect is we have to worry about especially at room temperature, we have to worry about electric field shifts from black body radiation. So that's a fancy way of saying thermal radiation that's in the lab. And this thermal radiation can give shifts. In fact, the shift of the frequency in most transitions goes as temperature to the 4th power. So if we go from room temperature about 300 Kelvin down to a millikelvin, we can totally suppress this black body shift, which is a real problem if we're at room temperature. So let's see. Okay, so anyway, after a very long time, we were able to get the perturbation of all the collision effect, black body shifts, et cetera, we'll get them down to a fairly low level. And around 2005, 2006, we got the mercury clock to have an uncertainty of about a little below a part in 10 to the 16. So this was done in 2006, and what was nice about that, we could get to an uncertainty in the frequent from all the systematic effects like black body radiations, collisions, et cetera. We can get all these so-called systematic uncertainties down to below a part in 10 to the 16. And in fact, this was we were happy because this was basically the first clock that had ever gotten below the performance of cesium. And in fact, through the years since the 60s, of course, cesium was getting better and better, but we could finally surpass the performance of cesium in these experiments. And these days, at least the people in standards lab, that we all talk about optical atomic clocks because they just, they can be so much better in principle than particularly, rather than as opposed to cesium. So I'm going to shift gears now a little bit. We certainly did a lot of nice experiments, I think, with the mercury ions, but we later switched to a singly ionized aluminum ion, and the wavelength of the clock transition there is around about the same as it is in mercury. But the nice thing in this aluminum ion is that the upper state lifetime is about 200 seconds, about 200 times longer than it was in mercury. And so that factor of 200 would give us a factor of 200 narrower absorption feature, which could be used to improve the precision of the clock. And these are the two Daves working on this experiment for more than 10 years now. So anyway, we were by the end of close to in 2019, we were able to get the systematic uncertainty, all the shifts due to black body radiation, et cetera, down to below a part in 10 to the 18. And so this kind of sets the standard again, that the cesium clocks are still a little bit better maybe than 10 to minus 16, but the optical clocks are just in principle so much better that this seems to be, at least for precision clocks, where the field is going now. So I'm going to say a little bit about the neutral atoms. I mean, I've spoken only about atomic ions here, but the neutral atoms are also very good. And in fact, a particular geometry that many of the neutral atom groups are using is that they'll have a standing wave field inside of a cavity. These light blue features are meant to represent the mirrors of a cavity, so that the radiation can be built up inside. This radiation is not at the clock frequency, but it serves the purpose. It's very much like the gives rise to the fields that trap an ion in this case, one simple way to think about it is that these fields, these are optical fields, and they work on the electrons in the outer electrons in the neutral atoms, and they make a trap, which is it's a trap for the electrons, and the nucleus is attached to the electrons, of course. Whoops. And of course, the nucleus is attached to the electrons. So we're basically trapping the electrons, which traps the whole atoms. And so the neutral atom groups that can make, you can think of these as pancakes you're looking on the side view, but there can be many trapping regions where the neutral atoms are trapped, and then they can probe the atoms in the same way, and certainly one big advantage is of the neutral atoms is that they have many more atoms, and so they can get much better signal to noise ratio in the measurements they do. So just I put up this reference. It's not the most modern reference, but anybody who's interested, you might jot this down, because this reference is nice because it covered all these different technologies, and there's certainly there's some modern references which show the better performance, but this is actually a good place to start. I would recommend if you're interested, and then you can find the more modern reference. Anyway, so. We were able to get down to about part 10 of the 18, and so what's the future? And one thing we are getting this much higher performance now, and so should we redefine the second? It's certainly much better than the definition-based, the accuracy and precision we can get with the ions on the optical transitions or the neutral atoms. Is much better. So should we redefine the second? And the reason nobody jumps to do that is because even though there are all these optical clocks that are better, there's no obvious winner in the optical. So people are reluctant, for good reason, not to change the definition, even though many of these optical clocks are better than cesium. And the reason for that is you don't want to change the definition of the second, then have to change it a year later because you found a better atom. So I think the standards groups that set the standards are wisely delaying on perhaps redefining the definition of the second. And I'll say that I'm going to say some words here that won't make a lot of sense by themselves, but basically, if we have, in the case of just take neutral atoms or many ions, we have basically the precision, the noise in the measurements we get go as basically the square root of the number of atoms, and so we have the signal noise goes as a number. So we, in terms of the measurement imprecision, for a clock, for a typical clock like this, the measurement imprecision goes down as 1 over the square root of the number of atoms. But there's certain kind of states we can measure. They're called squeeze states, and that whole topic is very interesting. But take me another lecture to go through to give you an idea what that's about. But they're basically they're entangled states, and they give this better measurement precision. So anyway, that's I think that's where we see a number of groups can see the improvement, but so far it hasn't been applied to an accurate clock. But I think that's going to certainly come at some point. So what other things can we think about? Well, we still think about navigation, and one interesting idea people have thought about is, for example, earthquakes, are always a precursor of earthquakes is there's strain on the earth, and so that's just a statement that say two locations that are on the surface of the earth are separated by kilometers, for example, their relative heights relative to the center of the earth will change due to strain, and if we could measure that strain, and certainly it occurs at a level of centimeters before an earthquake, or so that might be one application for potentially predicting earthquakes. And of course, there's just people are interested in mapping the gravitational potential around the surface of the earth. So there's lots of nice fundamental science we can think of. For example, what we and other groups have done is if we compare the frequency of two clocks that depend on different atoms or ions, the frequencies of those clocks, they depend on different mixtures of the strong, weak electromagnetic forces. And so if we saw the ratio of the frequency of the clocks changing in time, that would signal that the fact that maybe the basic forces were changing in time, and that would be real breakthrough. And in fact, we also, of course, this dark matter, gravity wave detection has been very prominent in the news over the last few years, and we have ways of we've devised ways of we might be able to use our accurate clocks to detect gravity waves. And also there's several possible mechanisms for detecting dark matter, which would tend to shift the frequencies, the fundamental frequencies of the atoms. And of course, it's it's always been a sport among physicists is can we find deviations from Einstein's theory of relativity? And so far the answer is no, we haven't. But so it's just his theory has endured up until the present time, which is pretty amazing. But anyway, we never as the precisions increase, we may be able to uncover some effects that signal new physics or deviations from what Einstein predicted. So I'm going to say a little bit more about, I've said about some of the effects that we have to worry about that give frequency shifts in our clocks. And I talked about thermal radiation. More commonly, a simple thing we have to worry about is all the ambient electric and magnetic fields inside of our apparatus are certainly not constant. So we have to worry about those effects. So other interesting effects, I've again, due to, Einstein, I told you about time dilation due to atomic motion, but there's also another effect comes out of Einstein's theory of general relativity, and that's so-called gravitational potential redshift. And it's basically, it's called a redshift because the gravity tends to shift the frequency of the transitions down, and for example, we can see those effects in distant star due to Doppler effect and so on. But anyway, so this is a kind of second kind of time dilation shift that Einstein came up with, and just to give you an idea that the redshift from the gravitational potential of the Earth at sea level is about a part in 10 to the 9, and so we have to worry about this, particularly if we go around. If we're trying to compare clocks around the world, we have to worry about their height, and more directly, we have to worry about their gravitational potential redshift. So it comes in at a very real level. In fact, in satellite navigation, it's a big shift. And so we have to worry about this gravitational potential redshift. So basically, I write down you can condense down this gravitational redshift and express it fractionally in terms of the gravitational potential and mass times speed of light squared. Anyway, this is fairly easy to derive. I won't go through here, but so anyway, we can measure these shifts, and one. It's not a big shift, and so just to give you an idea, just a little story here is, suppose you had a twin sibling and you were separated at birth, and suppose you live at sea level and your twin lives in Boulder, Colorado, about 1.5 kilometers above sea level. It turns out that after 80 years, your twin will only be about a millisecond older than you. So, and in our practical experience, everyday lives, it has negligible effect, but it certainly comes in. It becomes an important effect for our accurate clocks and the precision of navigation that can be done by the clocks. Oops. So anyway, actually, the history of measuring this gravitational redshift is pretty interesting. Actually, so not long after I went to Harvard as grad school, there'd been done experiment by Professor Pound and his student, I forgot his first name, Ripka. And anyway, their clock, it was, not the ones we usually think about. It was based on a gamma ray transition. A gamma ray transition in iron, and then this Mossbauer it's this using gamma ray transitions in atoms, nuclei actually, was pioneered a lot by Mossbauer. In fact, he received the Nobel Prize for this, for his work on these gamma ray transitions. Anyway, so in this experiment at Harvard, they basically had a source that would emit these gamma rays of iron, and then they would, I forget whether they went up or down, but as the gamma rays went up, they would lose energy, and therefore the frequency would shift, and they could measure then the shift in energy by, actually the way they measured it was just they moved the velocity of the receiver of the detecting atom up and down, and the velocity change would allow them to shift the frequency as they moved it up and down, and find when the resonances were equal. And anyway, they could measure the shift as the gamma rays went up in height over this just 20 meters roughly, and they got down to about a 10% level in this. So this was really a landmark, experiment that was done. Later, there was experiments that H. Maser clock was put on board a satellite, and a rocket rather, and there were others on the ground they could compare to, this rocket was basically they shot it up and it went down and splashed into the ocean. So during this time, of course, the velocity was changing, so they had to account for both the gravitational redshift and the time dilation due to the motion and due to the trajectory of the atoms. And they could they have different signatures, so they could separate the time dilation shift due to the gravitational potential redshift. And anyway, they could measure the effect down to a little better than a part in 10 to the 5. So anyway, just for fun in our lab, we decided we'd make a simple demonstration of the gravitational redshift in aluminum ions. So this was our aluminum clock. Doesn't look much like a clock. What you can see here on this table is this shiny tube is actually, that's our trap is inside this, and it has some vacuum components, but that is where the trap resides. But then all this other stuff you see on the table is just optics and lenses and mirrors and so on to guide, and lasers at the far end of the table to be able to do the experiments that the kind that I described. So this one again was on our single. This was on our single aluminum ion, which had this 220-second lifetime in the upper state. And so we call this clock number 1, and actually we have another apparatus which is which was as much identical as to this apparatus as we could do. It was actually in the room next door to what you see, the wall in this. It was in the room on the other side of this wall that you see in the picture here. So they were close by, and we called that clock number 2, and we would first do a measurement where we would measure the ratio of the frequencies of the clocks, and we could, after sufficient averaging, we could get down where we could show the frequencies were equal to. There was about error of 1 in this last digit to about a part in 10 to the 18. The ratio of the frequencies was 1. And then here, so this is James Chow, one of the people that was working with us at the time, and you can see what he's done here is he's put jacks underneath the table or clock number 1, and he raises the table up a little for a little while and he raised the clock about 30 centimeters, and we could measure the change in the clock frequency. It was about 16 parts about 40 parts in 10 to the 18, and we could see this effect, which was kind of fun to do. So we reported that in 2010 in the journal Science. But the optical clock guy or the neutral atom guys have done a lot better than we did in our simple demonstration. So, for example, there was a group in Japan that they had 2 separate clocks, and these optical lattice clocks, like I showed down here, and they had 2 clocks, and they could actually make, I forget where it was done, but the height difference in the 2 locations of the 2 clocks, was in this case 450 meters rather than the 30 centimeters we used, and they could actually make a measurement of the redshift to about 10⁻⁴ precision through the by comparing these 2 clocks at different heights. And then now the more modern experiments are so much better that I cite 2 groups here. This second reference is from our colleague at NIST in Gila, which is just down the street from NIST in Colorado. And there was a second group in University of Wisconsin, and they did essentially the same thing. But so they had these same kind of vertical optical lattice clock I was talking about before, and so what was amazing about this, particularly the second reference, they got down to where they could see the gravitational potential redshift down at the millimeter scale, and so they could measure it. It's not a very precise measurement, but they could measure it with uncertainties corresponding to on the order of a couple of millimeters, and just amazing experiment. And so anyway, this game will probably keep going on, but it's already at an amazing level, I think. So actually, it's just interesting to ask, well, what about the redshift from other sources? And so, just for fun, a while back I calculated, well, there's this. It's called I don't know much about astrophysics, but there's this cluster, this so-called galaxy cluster, the Virgo galaxy cluster. And it's a long way far away from it. It's about 54 light years, but the mass is about 10 to the 15th time the mass of the sun, and so it gives a relatively big shift, and that sounds like a problem maybe, but the issue is it's so far away that the gradient of the time dilation shift across the Earth and our local solar system is still extremely small, so that what you come away with is that around the Earth the clocks run a little slower due to this Virgo galaxy cluster, but all the clocks are in the vicinity of the Earth are affected the same way. That is, time is slowed down by this in the same way, so we just don't see the effect of the shift to the galaxy cluster, even though it's reasonably sizable. In fact, I should have said this earlier. The red shift at the surface of the Earth, or around the Earth, is about 5,000 times the red shift from the Earth itself. So it's actually a big effect. And they say we can't see it because it just means all the clocks are in the vicinity of the Earth are running at the same rate. So anyway, I'm going to conclude here, but I wanted to say that of course the important parts of any project like that are the people. So over the years, I showed the picture. When we started, we were 4 people, and at times we got up to over 30, including all the students and postdocs and visitors they had. So this was a picture taken at the end of 2018. And anyway, we certainly enjoyed. We got funding, although NIST gave us a lot of funding to do these blocks. Anyway, we got also money from the outside agencies, particularly, for example, Office of Naval Research. They want to be able to do better navigation, so they support this kind of work. But also, I must say, I was really lucky at NIST that we had great leaders, and for most of the work that I did at NIST, our leader was Catherine Gebbe, and she was later after she retired, then a younger person took over. And anyway, but we got a lot of support from them. In fact, what was nice for us, us four that were kind of leading this group, was that, I mean, they never told us what to do. They if we'd done something crazy, I'm sure they would have said something. But basically, we could determine the direction of our research, which was really nice. Anyway, so that it was really a great place to be. And with that, I'll thank you for listening, and thanks very much. And if you have any questions, I'll be happy to try to answer.
Thank you, Professor David, for such a wonderful and inspiring talk. Your talk is really a great addition to this event, and we know that our attendees will benefit from your insights. Thank you for agreeing to speak at our International Conference on Electronic and Photonic Integrated Circuits, EPIC 2022. We will now take a few questions from the audience.
Thank you, Professor. It's a really amazing talk and very good start to a day with so much events coming up with this kind of a talk. I have few just very basic questions. Like we measure long historical events very precisely with celestial events you just spoke in the beginning of your talk. So in terms of accuracy, how they are repeating even after so many years, like thousands of years, with so much celestial events, major celestial events happening in the space, how that repetition, how is that accuracy is matching with the atomic clock accuracy? And the second question is like, why we prefer this heavy atoms for your measurements, like you can have like lower with this aluminum also you can replicate that. So why the heavy atoms are mostly chosen? So
well, I think that the one simple answer for that is that, so for example, if we have if our clocks are in some sort of thermal equilibrium, then the relativistic time dilation shift goes as 1 over the mass. So the heavier masses for the same temperature push down the time dilation shift. So that's one reason. But I think it more has to do, aluminum is of course not as light compared to mercury, so that wasn't there's usually many other things that actually determine why we use one atom or ion versus another, and that's the mass is certainly a consideration, but there's so many other effects, how well we can measure the shifts of the transitions, and how well we can actually just implement the measurements of the frequency. So it's an important consideration, but it's certainly not the only one. So, but it's a good question. I mean, we do have to worry about that.
Hello. Yeah, actually, it's excellent. Really, the talk is, and of course, one point is that that wavelength, whatever you have considered, if we change the wavelength, then what will be the effect on the atomic clock? the measurement wavelength. Suppose-
Maybe I don't understand your question, because I mean, the wavelength is determined by the frequency, or at least for the clock, is determined by the frequency of the clock, right?
Yeah, so why particular that type of frequency you have considered in that, like in the lambda, which is, I think, in the visible or some range you have considered?
Yeah, I'm sorry, I just didn't understand your question. I'm having trouble hearing a little bit, so.
Yeah, actually the wavelength, whatever you have considered to measure the atomic clock, if what is the, like, if I change it, suppose by one nanometer, then what will be the effect on that?
I'm not sure exactly what you're asking. I mean, the frequencies of the transitions are fixed by nature, right? So, you know, we have to worry about the shifts that I've talked about, but as I say, maybe I'm just not understanding the nature of your question very well. Sorry.
Yeah, but suppose if you consider that same wavelength, whatever you are considering, in a different material, suppose, which have a,
Oh, I see.
a different transition, suppose, then what will be the effect on your atomic clock measurement? Suppose if it is not in that range, if it is about 1000 nanometer, you have taken a material which have a transition of 1000 nanometer. It will affect on the measurement? Or
Well,
it is
I mean, not, you know, fundamental, I mean, it does, because, you know, different atoms will behave in different ways, and they're subject to these environmental perturbations in a different way. But I would say that, you know, that in principle, we could, you know, we could run with almost any frequency. I don't know whether I said when I first introduced the mercury clock, one reason we choose why a high frequency transition is good is that basically the oscillations of the clock, then there's just so many more oscillations in a second. And so we can divide the interval of time, the second, into finer and finer intervals. So that's why we'd like to choose optical frequencies, higher frequencies than lower frequencies. But you know, aside from that, there's no, you know, fundamental reasons why we choose a high frequency or low frequency. It just has to do with the measurement aspects.
Yeah, thank you. Thank you. I understand. Thank you.
Any other questions? Okay, so if there are no more questions from the audience, let us give a big round of applause for the Nobel laureate speaker, Professor David Wineland. Thank you, Professor, for your time and effort.